Hi folks, in this video I'm going to talk about how to actually solve a game that's given to you as a payoff matrix. That is a zero-sum game that's given to you in the form of a payoff matrix, how you can actually find the optimal mixes for each player to use, and also the average payoff that results when each player uses their optimal mix. Right? So the average payoff to each player. As a simple example, we could take the game odds and evens. We know that that's a fair game, so we know that the average payoff is going to be 0. I'm going to denote that by capital V, so it's like the value of the game. It's the average payoff to the row player, so if it's advantageous, if the game is advantageous to the column player, then that value would be negative. If it's advantageous to the row player, that value will be positive. If it's a fair game, V will be 0. Right? And as before, I'll use M sub R and M sub C to represent the mixes that each player uses. So M sub R for the row player, M sub C for the column player. And we know that in evens and odds, there's nothing fancy to be done. You just try to keep your opponent guessing as much as possible, so each player is best off choosing his move completely at random, just choosing 1 or 2 fingers to throw with equal probability, but otherwise completely at random. So this would be the solution to the game evens and odds, right? Okay, that was easy enough, but how do we calculate the solution when it's not obvious, right? Well, that turns out to be a linear programming problem. So let's consider one particular example. Here's another 2-player game. Again, it's represented by a 2x2 payoff matrix, so again, a very simple game. It's no more complicated, really, than evens or odds. It just has a different payoff matrix. So in this case, notice that all the payoffs are positive, right? So the row player literally cannot lose. In fact, the row player cannot even break even. The row player always wins money in this game, right? So clearly this game is biased in favor of the row player, so it's safe to assume that the value of V is positive, right? That the average payoff to the row player is going to be greater than 0. Okay, that will be important in a minute in doing the algebra. Okay, now what are you trying to do? If you're the row player and you're looking for your optimal mix to play the game with, well, what you're looking for is a pair of probabilities, P1 and P2, right? Of course, probabilities by their nature have to be non-negative. In fact, they also have to add up to 1. We'll come to that condition later. But for the moment, we'll just say that they have to be non-negative numbers, right, the 2 probabilities. And then furthermore, as we saw in the previous video, if you multiply the mix vector M sub R transpose times P, what you get is the vector of average payoffs depending on what move your opponent plays, what move the column player plays. Now, if V represents the average payoff of the game to the row player, under best play, then the row player can guarantee that every one of his average payoffs is at least as big as that value V, right? That's what V means. It's the amount of money that's guaranteed on average to the row player per play of the game. So we got this constraint, right? We know that M sub R transpose times P should be greater than or equal to V. That is, every entry in M sub R transpose times P should be at least equal to V, right? Equivalently, we can write this by transposing everything. So if I transpose this product, then you transpose each matrix, but you also reverse the order of the multiplication. So you may remember that from linear algebra. If you transpose A times B, that's actually equal to B transpose times A transpose, right? So doing that gives me this. It's a completely equivalent multiplication. It's just that the result will also be the transpose, right? So whereas this would have been a row vector, this will be a column vector, but other than that, it's the same thing. And again, so equivalently, we can say that P transpose times M sub R has each entry greater than or equal to V. Right? So I'm just doing that for convenience. Actually, just to fit it more neatly into the framework of a linear programming problem, it's better to think of the constraint this way. So you'll notice that this is starting to look like an LP problem, a linear programming problem, in that what we've got here is a matrix of unknowns, right? The M sub r, that's the mix that we're trying to solve for, that's the unknowns, times some known matrix P transpose is greater than or equal to V. So this looks just like the constraint equation in a linear programming problem, or constraint inequality in a linear programming problem, right? So if you let A be equal to P transpose and the unknown X be M sub r, and you let C be the vector that just consists of V in each entry, then the constraint looks like this. It's exactly the same form as a constraint in the in a linear programming problem. But there is a problem here. There's a difficulty, an issue. We don't know what V is, and therefore, since we don't know what V is, we really don't know what C is. C is not a constant. C is also unknown. Okay? So this is actually a matrix inequality that has two unknowns rather than just one. Right? So I lied. This is not actually in the form that we find in the linear programming problem, because it has two constraints, two variables. C is also a variable. Okay, but there's actually a simple way to fix this. So I'm going to rearrange the variables a little bit in order to fix this problem. The trick is we take this constraint and we divide both sides by the scalar V, right? So if I divide C by V, I just get the vector of 1s. So, and I'm going to denote the vector of 1s by boldface 1, right? So divide C by the scalar V, you just get 1, 1. So that's this. And of course I have to do that to the other side as well. So I'm going to, so this constraint becomes 1 over V times A times X is greater than or equal to the vector of 1s, right? Now this is why it's important that V is a positive number, right? So remember previously I argued that in this case it's safe to assume that V is a positive number, because remember, if you multiply or divide by a negative number in an inequality, it changes the direction of the inequality. So it's important to know that V is a positive number here, and that therefore the direction of the inequality does not change from what it was over here. Okay, so we've got this, and now what I'm going to do is I'm going to basically incorporate the factor of 1 over V into the X. So I'm going to change my notion of what the variables are. Instead of the variables X being simply the entries in the mix, P1, P2, I'm going to say that it's those probabilities P1 and P2 divided by V. Right? So I'm incorporating the 1 over V basically into the X. As I said, X is going to be now 1 over V times M sub r. And of course C, now with the new definitions, is just this vector of 1s. So now we have the constraint in this form, again, with the new definitions of X and C, but now C is a constant, and so this fits nicely now into the scheme of linear programming, right? We've got one vector variable X. A is a constant. A is still just P transpose, right? Even after the change in definitions, A is still just P transpose. So we've got a constant, an unknown vector, and a constant on the right. And so the constraint is exactly of the right form. Now I'm also going to define a vector B to be a vector of 1s. And interesting thing to note here is that if you dot B times X, right, take the dot product of V with X, well, what do you get? That means you'd just be adding up the entries in X, right? If you dot a vector of 1s times any other vector, what you're actually doing is just summing that other vector, taking 1 times each entry and adding them all up. If I add these two entries up, P1 over V plus P2 over V, I get this, P1 plus P2 over V. And because the P1 and P2 are supposed to be probabilities, they're supposed to add up to 1, so this simplifies to 1 over V, right? So B dot X will be equal to 1 over V, okay? And now recall that in a linear programming problem, B dot X represents the objective function. That's the quantity that you're trying to minimize or maximize, right? And so that should be a variable. It should be something that can vary depending on the values of your unknown x, right? And in this case, let's see, now remember, we're working on this problem from the point of view of the row player, and v is the payoff for the row player, right? So the row player wants v to be as large as possible, and therefore the row player wants 1 over v to be as small as possible. So from the point of view of the row player, the goal is to minimize the quantity b dot x. Right? Also note that 1 over v is certainly positive because again, we can assume v is positive for this game. Right? It was clearly biased in favor of the row player, so v is definitely positive. So v will be maximized when 1 over v is minimized. Okay? So the problem then becomes, from the point of view of the row player, that we want to minimize the quantity 1 dot x, subject to the constraints that x has to have non-negative entries and that p transpose times x has to be greater than or equal to the vector of 1s. Right, so this is the particular linear programming problem we want to solve in order to find the best mix for the row player. Okay, and if we succeed in solving this problem, then we'll also be able to recover v, the value of the game, because as we saw, 1 over v is equal to b dot x, and that means v is equal to 1 over b dot x, right? So if we solve this linear programming problem, we'll also be able to get the value of v. v will be 1 over the 1 vector dot x star. By the way, x star, by convention, we use x star to denote the optimal value of x. The value of x you found as the solution to the linear programming problem, right, to the min or max problem. So in this case, x star represents the optimal x for this linear programming problem that produces the minimum value of 1 dot x, right? So v will be 1 over the 1 vector dot x star, and recall again that x was equal to 1 over v times m sub r. So if we want to get the optimal mix m sub r, we just multiply by the scalar v. So now that we know what v is from this, we can just multiply v dot x star, and that'll give us our optimal mix for the row player. Okay, so let's try actually carrying out that calculation. Actually, I'm just going to do this with Mathematica. So you want to solve this linear programming problem using Mathematica. Let's see, I think you can probably do that. Let me know in office hours if you need help with that. But I think that's it's just a straightforward linear programming problem that I've already showed you how to do that in Mathematica, but I'm happy to go over it again in the office hours. But if you solve it in Mathematica, this is what you end up with. The optimal x star turns out to be 1/10 3/10, and the minimum value of the 1 vector dotted with x turns out to be 2/5. Okay. So Mathematica will just spit out that solution for us. And then, because 1 dot x star is equal to 2/5, therefore we know that v itself is equal to 5/2. Okay? So, with optimal play in this game, that was clearly biased to the row player, but with optimal play, the row player should be able to guarantee herself an average of $2.50 per play of the game, right? 5/2 dollars, or payoff of 5/2 on average per play of the game. And finally, the optimal strategy for the row player we get by multiplying v times x star. So if I multiply 5/2 times x star, I get, let's see, I get 1/4, I get 1/4 and 3/4, right? And by the way, you can, good idea to perform a sanity check here. If your calculation was correct, these numbers will add up to 1 because they're probabilities, right? So that looks good. We probably did the calculation correctly because 1/4 and 3/4 do in fact add up to 1. Okay, so the conclusion is that the best mix for the row player is to play his first move 1/4 of the time and to play the second move 3/4 of the time. And if he or she does that, her average payoff will be 5 halves per play of the game, right? You see, let me go back and look at that. Where's the payoff matrix, right? So the best thing is to play this first row 1/4 of the time and to play the second row 3/4 of the time, right? I don't think that's so obvious from looking at this, right? You clearly want to mix the rows, right? Because if you always play the same row, then your opponent can choose a move which will minimize your winnings. Right? For example, if you always play move 2, then the column player can always pick his second move, and then your payoff will only be 2. And as we saw, with optimal play, you can actually guarantee your payoff to be 2.5, right? But you can only do that if you mix playing row 1 with row 2, right? And so the idea is that because you occasionally throw in row 1 as a move, the column player has to worry that if he just plays this all the time, he's going to be paying off 4 quite often, right? And so he has to compensate by sometimes playing his first column, right? So anyway, the optimal strategy is this. That's for the row player. So how do we get the column player's best mix? Well, we will use the same approach. We'll define our unknown vector x, right, that we're going to solve for in a linear programming problem. We'll define that to be the mix, the vector probabilities divided by v. One important difference, though, is that because v is the average value of average payoff for the row player, the column player would like to minimize v, right? Would like to pay the row player as little as possible, and therefore the quantity 1 over v, the column player would like to maximize, right? The column player would like this to be as large as possible. So for the finding the strategy for the column player, it's going to be a maximization problem. We're going to want to maximize 1.x. The other important difference comes from the constraint down here. Notice that the constraint for the problem for the column player goes the opposite way. That's because, let me back up a second here. That's because recall that the way you get the payoffs is that we wanted the average payoff. Oh, let me go back over here. We wanted the average payoff for the row player to be at least v, but for the column player, we want the average payoff to be no more than v. Right? Again, you have the opposite intention, and the other. And remember that the payoffs for the payoffs in the case of a strategy for the column player, instead of being m sub r transpose times b, it was p times m sub c, right? So, making those two changes, then in the problem for the to finding the column player's best mix, we're going to have p instead of p transpose, and the inequality is going to go in the opposite direction. Okay, so 3 differences when you're solving for the strategy for the best mix for the column player. It's a maximization problem instead of a minimization problem. We use p rather than p transpose, and the inequality in this constraint goes the opposite way. It's less than or equal to. And by the way, in both cases, this was all under the assumption that v was positive, right? And then, just as in the case of the row player, we have the same basic way for then obtaining the values for v and for the best mix m sub c. V is equal to 1 over 1.x star, and m sub c is equal to v times x star. Now, interesting point here. Because this problem, this linear programming problem to find the column player's best mix, is exactly the dual to the problem for finding the row player's best mix. Right? They're exactly dual problems that have exactly the same relationship that the dual linear programming problems have. And therefore, we can apply the duality theorem from linear programming. We can say that, therefore, both problems will have the same solution for 1 dot x, right? So in both cases, with the optimal value of x star, the value of 1 dot x star will be the same, and since this quantity determines the value of v, that means the value of v will also be the same. So whether you look at the game from the point of the row player or from the point of the column player, you get the same result. You get the same theoretical average payoff under optimal play. Now this is an important result because it simplifies the problem a bit. Without the duality theorem, it would be possible that the maximum for this problem, for the column player's problem, would actually be less than the minimum for the row player's problem. And that would mean that the v you got for the column player could actually be greater than the v you got for the row player. That means the row player would be playing a strategy to guarantee himself a payoff which is less than the payoff that the column player is working with, right? So the column player has a strategy that guarantees himself a payoff which is higher than what the row player thinks he can get. And this would lead to some confusion as each player might be trying to maneuver adjusting strategies to what would be non-optimal mixes in order to try to exploit the difference between the two numbers, right? I don't really want to get into that. I know that was a very vague description. You can ask me about that if you're interested in office hours, but I'm not going to get into it because it actually doesn't happen, right? Because of duality theorem, we don't have to worry about those complications, right? But it is good to know that whether you look at it from the point of view of the row player or the column player, you get the same value for the game, the same average payoff, and therefore that simplifies the whole study of game theory quite a bit, actually. Now, there's one other complication I should address. What if the value v is negative, right? In that case, well, then the algebra we did, let's see, when we performed that algebraic trick of dividing both sides of the inequality by v, we'd have to reverse the inequality. So we'd have a lot of inequalities that are reversed, and then we might not even have this preserved. We might have to change the sign of x's. It gets a bit messy. A simpler way to deal with the situation when the value of the game is negative is simply to reverse the roles of the row and column players, right? So a simple way to do that is first you take the transpose of the payoff matrix so that the rows and columns are reversed, and then you change the sign, right? Because in the payoff matrix, the payoffs are in terms of the payoffs to the row player. If you reverse the row and column player, you also have to change the sign of the payoffs, right? So every payoff, positive payoff to a row player now becomes a negative payoff to the column player, right? So change the game by forming a new payoff matrix, which is just the negative transpose of the original one. It's really the same game. The rules are really identical. It's just that we've reversed the row and column players. But because of doing that, we've now made v positive, right? So v, which was the payoff to the row player, was negative. But now, because we reversed the role of the row and column players, v is now going to be a positive payoff to the new row player, who was the old column player. I know this gets confusing. Sorry about that. So okay, so we work with a modified form of the game. It's really the same game, but we work with the new matrix. I'll call it p prime, which is just negative p transpose, where p is the original payoff matrix. And then we solve this game in the usual way. And after you get the solution to the game with p prime, then you reverse the mixes, right? So the mix for the column player in p prime becomes the mix for the row player in p, and vice versa, right? The mix for the row player, what did I say that? The row player in p prime becomes the mix for the column player in p, right? And also change the sign of v, because of course p prime had a positive v, whereas we know p had a negative v, so we just changed the sign of the v that we get. So if you do all this and then carry out the formulation of the linear programming problems and everything. I just summarized it here. To save room, I left off the condition that the vector x has to be non-negative, but that's true in both of these problems, right? Where I'm assuming x is a non-negative vector. Okay, so to find the best mix for the row player in the original game, right? The original game defined by the payoff matrix P, what you do is you minimize 1.x subject to minus P transpose x is greater than or equal to 1. Right? And to find the best mix for the column player, you maximize 1.x subject to minus P times x is less than or equal to 1. Right? So notice that I basically here, the main difference is that I changed the sign in the constraint here. Instead of having positive P transpose and positive P, I had negative P transpose and negative P. And then the other difference is that after you solve these problems, in order to find V, you just change the sign, right? So the V in the modified problem would be B dot x star, but that means the V in the original problem would be minus B dot x star. And that the mix would be well, we'd want to take the V in the modified problem, which was the negative of the V in the original problem, right? So the negative V here would be a positive number, right? And then we multiply that times x star in order to get the mixes, whether it's m sub r or m sub c. You do it the same way, okay? I know that's needlessly confusing, but it's a question of reversing the row and column players, reversing signs. It gets really confusing. It's just not difficult. It's just a bookkeeping issue, really. One other case of V we should consider. I mean, we've considered the case when V is positive and when V is negative, but what if V is equal to 0? What if the game happens to be fair and the average, expected payoff with optimal play is 0? Well, unfortunately, in that case, 1 over V would be infinity, right? And so whether we're maximizing or minimizing, there would be no solution, right? If you're trying to maximize or minimize 1.x, right, which is equal to 1 over V, then if 1 over V, if the optimal value turns out to be infinity, then there's going to be no solution either way. So that's why I wanted to start with a game that wasn't fair. The first example I did of solving a game was a game that was clearly biased in favor of one person. You might think that fair games would be the easiest ones to work with. You might think that 0 is an easy value to work with, but the peculiar algebra of these problems means that actually fair games are the most awkward to do formally. And so the way you recognize a fair game is if the linear programming problem does not have a solution. Okay? Okay. Now, the one important thing we noticed in this previous example, I started off with this game. This was the payoff matrix from the example I just did. So it was all positive payoffs, and as we saw, it has an average payoff of 2.5 to the row player. So if they're betting, if these numbers represent payoffs in dollars, then the row player is going to make an average of $2.50 per play of the game, even with best play, right? Well, best play by both players. So it's very, very biased in favor of the row player. We could turn this into a fair game simply by subtracting $2.50 from each one of the payoffs. If we do that, we get this, right? Now this is pretty clearly a fair game, right? The payoffs seem nice and symmetric here, right? And in fact, it's pretty easy to convince yourself that if you simply subtract a constant, add or subtract a constant from each one of the payoffs, it does not affect the strategies. It does not affect the optimal strategies or the optimal mixes for both players, right? You could think of this constant sum or difference that you're adding or subtracting from each payoff. You could think of it as a kind of an entry fee to play the game, right? So maybe what happens is that the row player has to pay $2.50 in order to be able to play this game, right? He has to pay an entrance fee of $2.50. That entrance fee would not affect the strategy he would then use in playing the game, but it would affect his net winnings, right? You'd have to subtract 2.5 from his net winnings. So this trick of adding or subtracting a constant to each payoff means you don't affect the mixes, the optimal mixes. You only affect the average payoff. So by subtracting 2.5 from each one of these payoffs, we have a game which is now fair, but it has exactly the same strategies as the original game. Okay, so exactly the same best move mixes as the original game did, right? So this is also a game in which the rogue player is best off playing row 1 1/4 of the time and playing row 2 3/4 of the time, right? But now the average payoff is going to be 0, so this is now a fair game. This trick of adding a constant to each payoff is a very useful trick in order to bias a game to make sure that it has a positive v-value, right? If you're not sure about the value of a game, what you could do is you could add a constant to each payoff to make sure it's sufficiently biased that the average payoff will be positive. And then you'll know exactly what linear programming problem you need to solve in order to find the optimal mixes. So, very useful trick. If you're not sure of the sign of v, or if you think it might be equal to 0, just add a constant to each payoff to make sure the game is sufficiently biased that v will be greater than 0. And then you can just solve it as we did in the previous example, right? Because the modified game will have the same optimal mixes, but the payoff v will just differ by the constant that you added. It's like an entrance fee, right? So you just subtract off the entrance fee from the value you got for the modified game, and that will give you the value of the original game. Right? So let me do an example of that. Okay, having done all that theory, I'm sure you're tired of theory. I want to now do a concrete example, and in order to prove to you how reasonable these calculations actually are, I know it may sound very confusing right now, but at least when you have a relatively small, payoff matrix, these calculations are actually easy enough to do by hand. I mean, you don't even need a computer to do them, and that's what I'm going to do for you right now. So let's consider a two-player game that has this payoff matrix, right? Now notice that the row player has 3 possible moves and the column player has 2 possible moves. However, the payoffs look kind of evenly distributed. In fact, if you add up all the possible payoffs, they add up to 0. So you might think, this might actually be a fair game. On the other hand, it is true that the row player has more moves to play than the column player, so in some sense the row player has more is more flexible in his possible strategies than the column player. So it might turn out to favor the row player. But the upshot is we can't exactly be sure what the value of this game is. So we will use the trick of solving for, adding a constant to each of the payoffs, right, as described previously. So what I'll do is I'll just add 2 to each one of these payoffs. So we get the new payoff matrix P prime, which has all non-negative entries, and it's pretty obvious that P prime favors the row player, right? So I think we can safely assume that the value V prime of the game P prime is positive, is strictly positive. And therefore we'll be able to use the strategies we described earlier for solving games that have a positive value, a positive expected payoff. And as I said, I'm going to do this without using Mathematica. I'm going to do it purely with pencil and paper. So let's get started. Recall that when you're solving a game like this, you want to figure out the best mixes for both players. And that means you're solving 2 linear programming problems. Before we dive into one of them, let's compare those 2 linear programming problems. The problem for the row player is going to consist of a problem with 3 variables, basically. In other words, our x will be a 3-vector, a 3-dimensional vector, right? In terms of the mix, we're looking for a probability for playing the first move, and the probability for playing the second move, and the probability for playing the third move. So basically, we've got 3 variables there. The problem for finding the best mix for the column player would only have two variables, right? Now that doesn't make much of a difference if we'd be using Mathematica, but since I'm insisting I'm going to do this without Mathematica, I would really rather solve the problem with two variables, right, than the problem with three variables. So I'm going to solve that one first, because that one is simpler. It only has two variables. So the first thing I'm going to do is I'm going to find the optimal mix for the column player. I'm going to find m sub c. Okay, so we know that the value v prime for this game is positive. We're looking for the best mix for the column player, so I'm going to I'm going to solve the linear programming problem that I indicated earlier. We want to maximize the one vector dot x subject to x is non-negative and p times x is less than or equal to 1, right? The vector of all ones. Okay, so we're trying to solve this problem, maximize 1 dot x subject to x is non-negative and px is less than or equal to 1. Let's translate this into a finite problem, right? In finite, they don't do these problems by formulating them in terms of matrices. They just formulate them in terms of basic simple algebra, right? High school algebra. So if I let x be equal to x1, x2, right? So with the x1 and x2, little x1 and little x2 are the components of the vector x, then this problem here becomes maximize the sum x1 plus x2 subject to the conditions that x1 and x2 are both non-negative, and we have these inequalities, right? So these come, you notice that the coefficients here come from the payoff matrix, the modified payoff matrix, right? 3, 0, 1, 3, 3, 2, right? Exactly from the modified payoff matrix there. And then they all have to be less than or equal to 1. Okay? So, as I said, this is just a finite problem. So I'm going to solve it like we do in finite because I'm pretty good at that. I've done that a lot. If you graph these inequalities all in the same graph, then it looks like this, right? So I've got these lines, I've got this horizontal line, this is the line 3x1, or 3x equals 1, and I'm using y for x2, right? So x1 is the x-axis, x2 is the y-axis. So these are my three lines, and then the inequalities are the shaded regions. The feasible set, the set of points that satisfies all the constraints, including the non-negativity constraint, is this dark four-sided region here. So that's the feasible set. Now the objective vector is the vector of 1s, right? 1, 1. So it points right down the middle of the first quadrant, right? It's exactly the diagonal between the x and y axis. We're trying to maximize the dot product of that vector times the point in the feasible set. So what that means is we want the point in the feasible set that's farthest in this direction, farthest in this up to the right direction. I'm going to call it the northeast direction, right? So the point in the feasible set that's farthest to the northeast would be this point here, right? That's the point we want, right? That's going to be represent the solution to the linear programming problem. Well, that point is formed where the two slanted lines intersect. So the two slanted lines come from these inequalities, and therefore this point of intersection can be determined by solving the system of these two equations, right? These are the two equations for those two lines. It's easy to solve. What you wind up with is that x1 equals 1/7 and x2 equals 2/7, right? So with that solution, we can now find that, well, if we add them together, their sum is 3/7, and the sum, x1 plus x2 equals 3/7, well, that represents 1 over v prime, and therefore v prime, that is the average payoff to the row player in the modified game, is 7/3, right? Now, taking our v prime and multiplying it by our solution for x, 7/3 times this vector 1/7, 2/7 gives us the mix for the column player, the optimal mix for the column player, turns out to be 1/3, 2/3. Again, do the sanity check. Do these numbers add up to 1? They should, because these are supposed to be probabilities, and yeah, they do, so that's good. So it looks like maybe we did this correctly, right? So it looks like the optimal strategy for the column player in this game is to play his first move with probability 1/3 and his second move with probability 2/3. And in that case, if he does that, then the average payoff to the row player will be 7/3. Now, remember, this is the average payoff in the modified game. The game was modified by adding 2 to each one of the payoffs, so we biased it in favor of the row player. It's like the column player had to pay a $2 entrance fee in order to get in the game. So therefore, the average value in the original game would be the payoff in the modified game, 7/3, minus 2, right? So I'm going to subtract off the 2 that we added on to modify the game. And now we can say that the average payoff in the original unmodified game would have been 1/3. Okay, so it turns out, let's go back and look at the original game. It turns out the original game did in fact favor the row player, because we just saw that the average payoff with best play is 1/3 to the row player. So on average, the row player will make about 1/3 of $1 per play of the game, right? And as I said, we might have guessed that because we saw that the row player had more flexibility in choosing his moves. The row player has 3 choices in choosing his moves. The column player only had 2. So it does seem that the row player has a kind of an advantage here. And in fact, if you just restrict your attention to the bottom 2 rows, it does look like the row player has an advantage if you forget about the first row, right? If you ignore the first row, it does seem that the row player has an advantage if he just restricts his attention to the bottom 2 rows and never plays row 1 at all, right? And so it turns out that the row player has a systematic advantage in this game. The best thing for the column player to do, as we saw, is to play his first column 1/3 of the time and to play his second column 2/3 of the time, right? He really doesn't want to play the second column too often because he runs the risk of a big loss here. On the other hand, in a sense, it keeps the row player honest, you could say. Is that the expression? Because if the column player only played row 1 all the time, column 1 all the time, then the row player could make an average of $1 per game by only playing his third move, right? By only playing row 3. So the column player has to mix it up a bit to keep the row player from winning $1 all the time. Okay, but the optimal mix turns out to be 1/3 column 1 and 2/3 column 2. Okay. Now, let's move now to figuring out the optimal strategy for the row player. In order to solve this, I'm going to make use of another aspect of the duality theorem, complementary slackness, right? If you take the solution we just got for the problem for the column player, and you plug them into the constraints, let's plug in these values 1/7, 2/7 into these constraints here, what you find is that we get exact equalities in these two, but this inequality is slack. 3x1 is strictly less than 1 when x1 is 1/3. So this inequality becomes slack. In fact, you can see that visually in the picture, right? We know that the solution corresponds to this point. This constraint corresponded to this horizontal, this vertical line, and this point does not touch the vertical line. It's in the interior of this inequality, right? It's not on the edge. It's in the interior of that inequality. So that corresponds to the fact that this inequality is slack at the solution. Now remember, complementary slackness tells us that the corresponding variable in the dual linear programming problem will turn out to be 0 in the solution. Right? Now, so what does that mean? Now remember, this inequality corresponded to the first row in the matrix. And the first row in the matrix corresponds to the variable, or the percentage of time, or the fraction of the time that the row player will play move 1, right, in the dual linear programming problem. So the conclusion is that the row player should never play row 1. He should just ignore it. right? Then he should play row 1 with probability 0. So that's a big help in solving the dual problem. We now know that in the dual problem, x1 is going to be 0, and so we can ignore the row player's first move. That means when we're solving now the problem for finding the mix for the row player, at first we thought that was going to be a three-variable problem, but now because of complementary slackness, we were able to eliminate the first variable. So now we can just look at the remaining two variables. We can just look at x2 and x3, right? In other words, the variable for the second move and for the third move. So the dual problem, solving for the optimal mix for the row player, is minimize 1.x subject to x is non-negative and subject to p transpose x is greater than or equal to 1. Now, at this point, we now know that v is greater than 0, right? So what I think I'll do for the sake of simplicity is I'll just go back and use the original matrix P. We now know that in the original matrix P, the value v was positive, so there's no need to, any longer to work with the modified game, right? We can just go back to the original game because we know that one actually did have a positive p value, right? And so we can use all the theory we developed earlier when we know that the value v is positive. So the problem is minimize 1.x for a non-negative vector x subject to the constraint that p transpose x is greater than or equal to 1. And again, if you translate this into high school algebra, right, using noting that the x vector consists of the variables x2 and x3. Remember, we don't need x1 because we know x1 is going to turn out to be 0. Then this problem becomes minimize x2 plus x3 subject to the constraints that the two variables x2 and x3 are non-negative, and they satisfy these two constraints, that negative x2 plus x3 is greater than or equal to 1 and x2 is greater than or equal to 1. And remember, these last two constraints, they come from the payoff matrix. So in the payoff matrix it looked like, let's see, the original one looked like this. Remember, we're ignoring the first row, so we're only using the constraints that come from the second two rows. So it says negative 1x2 plus 1x3 is greater than or equal to 1, and 1x2 plus 0x3 is greater than or equal to 1. So that's where these two come from. Oops. Here, right? Okay, so now, solving this problem, again, I'm going to solve it like I do in finite. I'm going to graph these constraints. So when you graph all the constraints, let's see, we've got this constraint corresponds to a vertical line. Again, well, I'm using x2 to be the horizontal variable and x3 to be the vertical variable, okay? So x2 equals 1 would be the vertical line, right? X equals 1. And then this I'm graphing as the line negative x plus y equals 1. That would be this line here, right? And then I also they have to be non-negative. So once again, the feasible set is actually just this dark blue region up here that satisfies all four of those constraints. Once again, the objective vector is just 1, 1, right? The objective vector is just 1, the vector of 1s. So it points this way. But now we want to minimize, so we want to find the point in the dark blue feasible set that points the most in the opposite direction to the objective vector. So points most in the south, I should have said southwest direction. Okay, I'll fix that. It points most in the southwest direction, right? And that would be this point here. This point is formed where these lines intersect. So we find the solution. The solution is even simpler than the last one. It's just 1, 2. So x2 equals 1, x3 equals 2. The sum, x2 plus x3 is equal to 3, and remember that's going to be 1 over v, so therefore, once again, we get v equal to 1/3. That's reassuring, right? We got the same value for v that we got previously when we solved for the column player's best mix. Very encouraging to get the same result both times, as we should by the duality theorem, right? So v is 1/3, and then when we multiply v times our solution for x, right? X was 1, 2. Multiply that times 1/3, then we get the mix. Oh yeah, the mix over here that M sub r, the best mix for the rope player, is 0 probability of playing move 1, 1/3 probability of playing move 2, and 2/3 probability of playing move 3. Right? So, like I said, it turns out you can actually do problems with a small payoff matrix without even using Mathematica. It's actually quite easy, especially if you exploit complementary slackness. Right, that can be really helpful. I got to admit, this problem would have been harder if it had been a 3x3 payoff matrix. Then there would have been no way to avoid working with 3 variables. So anyway, this is the kind of a typical thing that I do on homework and exams. So you don't have to worry about facing a 3x3 matrix on an exam. This would be the hardest sort of problem I'd give you as an exam problem on game theory.